Welcome to Module 4, Tutorial 4.1, Parametric Tower Massing. So at this point, you've covered a lot of ground. You've gotten comfortable with Grasshopper interface, you work with points, curves, surfaces, and you've started to understand, hopefully, how to work with lists and beginning to think about data structure. And you've also seen how attractors can drive variation across your geometry. So you've had a really good base to start working with. Now in this module, we're going to take all of that and apply it to something more architectural. We're going to be building a tower, and one of the things I want to do in this module is to start looking at how some well-known buildings over the past few decades have actually used these exact same tools in their design process. So we're going to be working with the Absolute Towers by MAD Architects. MAD is a Beijing-based practice founded by Ma Yansung, and these towers, which are built in Mississauga, Canada, became really iconic because every floor plate is an ellipse that rotates slightly as the building goes up, so giving it this fluid twisting form. You might have heard that they're called the Marilyn Monroe Towers, and this was one of the early projects that really used parametric tools like Grasshopper to drive the massing logic of the building. And once the first one was built, the second one was just variation of the same Grasshopper definitions. So if we look at the general floor plane, and in this case, you'll see that they're variation of an ellipse structure. So we're going to begin by assuming that this is an ellipse floor plate that we can then manipulate. The final output of this tutorial will look like this geometry on the left, which would allow us to learn a number of transform operations and list management tools. Our first step is to construct a new Rhino template. And I'll open a new Rhino file, and I'll be working in small objects feed. Go to my perspective view called Grasshopper, and our first component will be an ellipse component, which will be the template for our floor plates. Ellipse is a type of curve. It's stored under primitive components, and look for an ellipse component which is using a base plate or a base center for the ellipse, then radius 1 and radius 2. If I look at the center, we do see a circle, so ultimately a circle is an ellipse with the same radius 1 and radius 2. You can hover over the values and check this. So please pay attention that my plane is scaled down, so this is a setting we can adjust under our display menu, under preview plane size. When you first open Grasshopper, this value is set to 8. Which then generates this really large, basically plane or a frame for your geometry. I recommend adjusting that, and you can always just override that with new values. So go to your display menu, go to preview plane size, and you can adjust this. I usually keep this 2.5. And you want to make sure that when you change the value, you enter, and you'll be able to then see the result. So we're going to keep the center as is. So this is set to a world origin, which is at 0, 0 with x, y directionality. Then we're going to make a slider that goes from 1 less than 100. And I'm going to adjust slightly. The values that I'm using for this definition is based on the general reading of the floor plans as much as I could find, and then also some of the values are based on the proportions that I found on the images. So the values will represent as close as possible the actual tower. So I'm going to be using two values here, radius 1 and radius 2. For radius 1, I'm going to drag the slider all the way up to 100, and we're going to connect this to radius 1. You'll see that that's quite an adjustment, the way that your plate is stretching. A copy of the slider and change this value to 75. You can do that by either scraping the slider to that number, or you can always just double click and enter the number directly. And then connect that as radius 2. Our next step is to duplicate this ellipse and make sure that we are able to generate the tower, which has a total of 56 floors. So for me to be able to copy this multiple times, I need to begin to actually recreate the same ellipse a number of times. And in Rhino, if we were to do this without Grasshopper, you would be able to do multiple copies. In Grasshopper, concept of move and copy are the same thing, as you are always creating a history or a trace of your previous object. However, as you can imagine, it's not very optimal for me to move this 56 times, so we need to come up with a way that by manipulating our data structure, we can actually achieve this with a fewer number of steps. So let's think about this as two steps. One is this idea of moving the floor plate. As I mentioned, moving and copying is the same thing. And then the second information is how many times. So in this case, 56 times. So if we think about this as a combination of data and action components, the action in this case is the move component. So let's go ahead and find that under our transform tab, under Euclidean, and we'll find the move component. And what it is that I want to move is an ellipse. So connect the ellipse to geometry, and you'll see that it has a preset vector of 10 values here. Based on the drawings, I've assessed that the floor to ceiling height is 15. So I want to adjust this vector by overriding it using components. So this will require two components. One is a vector in z direction, another one is the amount of moving. So let's go ahead to our vector tab, our vector subtab, and first construct a unit z vector. So a unit z vector is a unitized vector, so it only has a multiplication of 1. You'll see that we're only moving this one value. And the second information is by how much. And in this case, this is 15. I can, in this case, use a combination of a panel or a slider, but let's rely on a slider here. So I'm going to double click on canvas. I'm going to make a slider that goes from 0 less than 15 because I want to stay on that number, and then 20. So 0 less than 15 less than 20, and connect that to your floor plate. So let's begin to do some naming here. I'm going to group the ellipse to the slider and say this is our base floor plate. And then we have the moving operation. So this is move for. Feel free to adjust the writing as you see fit. This is for our own reference. Now, the next step for me is to figure out a way where I can do multiple moving. I'm not going to copy this 56 times. So let's start to understand what the data structure is here. Let's grab a panel. So double click on canvas, use a quotation mark. So in this case, I have an ellipse. Then with to that ellipse, I'm providing one vector of movement. And what that is resulting is an ellipse that moves in place, right? So the output of our original ellipse and our final ellipse in our panel looks the same. But let's think about it as, in this case, we're taking an ellipse, we're matching it to a vector of movement, it gives me a new ellipse, right? So beginning and moving. The way that Grasshopper works, it is taking advantage of the data structure. So in this case, if we look at structure of a panel, I have a single element within a list. And you can always tell that it's a single element because it's displaying it with single wires. What is within a list is the content. So in this case, it says it's an elliptical curve. It's using an index. So we're starting always to count from item 0 and then the path, right? So it's matching one ellipse to one vector. It provides a moved ellipse. However, if we adjust number of elements within a list, the outcome is going to be different. And this difference is based on some default assumptions that Grasshopper makes about the file, and then there's ways of manipulating that. So as a general rule, Grasshopper always favors however many elements you have within a list, but it always favors the longest list. So let's think about what this means. For now, I'm going to take the slider of my move floor. I'm going to make a copy of this. And let's say instead of 15, I'm going to adjust this to 20. And I'm going to now provide another value for a vector of movement. Grasshopper by default only takes one input, so if I just replace the wire as is, it is going to replace the default. However, it is possible to connect more than one slider to an input. I'm going to zoom in a little bit so you can see this better. If I hold on Shift while I want to drag a wire, you see a green icon appearing with a plus sign. So hold on Shift, then drag your second slider to the input of our unit Z vector. And what you'll see immediately is that in the panel of our vector, there's two vectors that's displayed here. Vector 1, which is represented the Z value with the first slider, and vector 2, which is represented with the second slider. The order that these numbers appear in a list is directly correlated to the order of connecting these wires. So what do I mean by that? If I go to the factor here and tell it to disconnect all, and let me now connect 21st, right? So in this case, I want to move 21st, then I want to connect 13. So again, let's hold Shift, and you'll see that now it displays the 21st, then 13. This is not based on whichever number is smaller or larger, right? It's based on whichever one is connected early. Now, would this matter? Yes, depending on how you want your operation to be executed, perhaps it matters which one is connected first and which one is connected second. And let's also pay attention to the wires. Here we're starting to see again how our representation of wires are changing based on however many elements we have within a list. And in data structures, we often care about whether it's single or more than one. So one, we are displaying it with single wire, and more than one, you do see this double wire. Please remember that if you don't see the difference between wire, this is a setting under our display menu called Draw Fancy Wires, and you always do want to have that checked. Otherwise, you're going to miss quite a lot of cues that Grasshopper is giving you about our data structure. So now that we know that there's a way that we can manipulate and create more than one, as I mentioned, I have 56 floors. So do I copy this 56 times? Well, that's not efficient, but it's possible. So let's try it one more time. I'm going to make another copy of the Z slider. Remember that we need to hold Shift to connect, and there it is, right? So I'm able to then continue doing that. So what that tells me is that if there's a way that I can have a list of vectors, I can then move this multiple times. Now, why is this happening? Remember, I mentioned earlier something called favoring the longest list. So if we do look at the output here, we have one ellipse. It's the same ellipse that I can control its radius 1 and radius 2. But Grasshopper, when it compares lists, it always favors the longest list, meaning what I'm telling it to do is to move, and it's grabbing this information from an ellipse. So one ellipse, then it goes and finds the first vector of movement. So then it performs that first one. Then it wants to repeat this as many times as your longer list is. And your longer list could be either geometry or a vector of movement or any number of operations. So we'll see quite a few examples of that today with the operations that we're doing. So as you can imagine, this is not an optimized way of working. So I'm actually going to delete these two. And I'm going to change the slider back to 15, since that is the floor to ceiling height that we want to achieve. We're going to look for another component, which is called series, for us to create series of numbers, as the name indicates. Let's go to our sets, And in sets, we have the second menu called sequence. And here you want to look for a component called the series. So this component, the color is darker and means that it doesn't have any default, let's say, preview. But let's go ahead and grab a panel and see what it does. Let's first understand what it does, then we'll go ahead and manipulate the data. So it seems like it's giving me quite a lot of numbers that it starts from item 0, goes all the way up item 9. So remember, this value on the left is the index number, then this is the content. So in this case, they happen to be the same thing. So what this has is a start number. I'm going to make a slider that goes from 0 less than 5 less than 10, and I'm going to give it 1 point decimal. 0 less than 5 less than 10 with 1 point decimal. So the start number is the first number that you see, right? So it used to be 0. Now I can increase this to any number you want. So this start number is the starting number of your list. The step number is the step value is how each value is being increased. So in this case, it's clear that every time we're adding one value to our list. So the step value is set to 1, but I can also adjust that. So if I change the step value to 2, every time from that starting number, whatever that might be, I'm adding 2 values to the previous number, and that's how I'm generating the list. And this last component here is how many times I need to repeat this. So this is set to 10, and this is number of times that we're repeating, so this needs to be an integer. Let's do 0 less than 20. And if I just tell it to repeat once, it will just take the start number, and that's it. As I increase this, you can see that I am increasing number of elements in the list. So as you can imagine, with something like this, when we have a uniform spacing such as the floor to ceiling distance, we can easily generate a number of, in this case, vector values. For those of you who are familiar with maybe a computational design, there is this concept called a for loop. A for loop is exactly what a series does. You have a starting number, you tell it what is the spacing between each iteration and when to stop. You might have heard of something called an infinite loop, and an infinite loop is a loop that doesn't have, let's say, a stopping value. So think about a series as a for loop in Grasshopper. And that is the interesting part of learning Grasshopper, that it actually gives you an understanding of computation in general, and you can apply this to your future, let's say, syntax that you might be learning in different languages. Okay, so with this in mind, let's go ahead and adjust this so that it's suitable for what we want to do. In this case, for the starting value, I'm going to keep this at 0, since I want to make sure that my starting floor plate is planar. The step size, however, the step size is the 15 that we have determined, which is our floor to ceiling height. So I'm going to actually connect this, and I can remove this from this group so we can organize it later. I'm going to select the slider, right click on the group, tell it to remove from group, and I'm going to delete this, and I'm going to use this as the steps size. So every time we're generating 15 values between. At this point, actually, to not make it confusing, I'm also going to separate the number 15 from the unit z. So to disconnect, remember we use an operation on which we can right click and go and disconnect, or you can also use control and drag the wire and disconnect. So when you hold shift, you're able to add multiple. When you hold control, you're able to disconnect. So let's leave this here. I'm going to start to also name these. So our starting value is 0. So this is, I'm going to right click and write this. This is height of the first floor. Then this is my floor to ceiling height. And all I'm doing is just right-clicking on each slider and changing the description. And it will eventually help me when I want to control this. And then the count is how many times I want to repeat this. If you remember, I said that we have 56 values, so this slider does not go all the way up to 56. You can either generate a new slider or edit this. Let's edit. If you right-click on it, you can go to values, and here you can change the end value for this. Let's change the end value to 100 so we can try when we were first experimenting with this. And the value that you want to stop on is 56. So now I'm able to, when I look at my list, this would go from 0 to 55. So we're always counting from 0, so that's a total of 56 values. And with our series component set up, I'm going to just make this a little bit smaller. And I'm going to group this to itself and say these are our two ceiling heights. And we're going to then connect this to unit Z. Now, I can either go directly from the panel or from the series component. It really doesn't matter. I'm keeping the panel here for us to be able to use it as a reference later on. So in this case, I'm going to bypass the panel and go directly from the series. And as soon as you connect this, you'll see that, sure enough, your floor plate is repeated 56 times. While we're here, let's do some experiments together. So the first value, let's look at this. You can see that that's the first value that is being shifted from, in this case, floor plates up. The second value is the step size, which is spacing between each of the floor plates. So you can see that as we change this, the spacing is being scaled up and down. Let's make sure we leave this at 15. And the last value here is the count. So how many times this is repeating. So less number, this, you can see that it's repeated less. But with this, we should easily be able to then replicate however many floors we have, right? So make sure that we end with 0 value for start of the first floor, if the spacing is 15, and the last value is 56. And last thing, I'm going to group all of this together. And I'm going to, I can either incorporate this within the floor move or create a new group. I'm going to add this, so this way we can also take a look at that. So I want to include the entire group within our move group. So select the group that you want to add, right click on the group that you want to add it to, and there it is. Now, as you can see, we're starting to have a lot of panels. These are optional, and often it's there for you to learn what you're doing better. And you can determine if you want to keep them or not, but it's not going to really affect your final definition. And also remember that at any point you can also begin to change the color of your grouping. In this case, if you feel like if you want to keep all the colors the same and introduce maybe text in a different way, you can go ahead and do that. But at any point, you can either move them individually, or let's say if there's a color that you like. So for instance, I changed this color and I want to use it for my grouping going forward. I can also set that as default. And let's say I want to change the color of this group. Unfortunately, there's no way for me to reset the default, but I can regroup it here, Control G, and now I'm able to match the groups. For the sake of this assignment, it really, the grouping color and the naming is not important, so just make sure that it's set up in a way that you're able to understand. Our next step after this is to introduce a rotation and this twisting to this tower. And the rotation that we're going to be using is a component under transform, under Euclidean. And we're going to use a rotation component that is using the base plane as the starting point. So let's transform Euclidean rotate. Let's look at the components of this. It's asking for a geometry, it's asking for an angle, and it's asking for a rotation plane. So the geometry we want to move is, the geometry that we want to rotate is all the geometry that we've already moved, and each of them I want to be able to provide a different rotation. If I connect this as is, your entire all the floor plates will be moving, right? So this is your move component, this is your rotate component. And the amount of rotation, if it's overlapping, the amount of rotation is 90 degrees. And this is a preset that we have in our angle input. And by default, your rotation or all angles in Grasshopper will be set to radians. If you're more familiar working in degrees, and for this assignment we're going to be working with degrees. And this 0.5 is preset, 0.5 times pi. And we can definitely replace this. But before I replace the angle input, I'm going to right click on the angle and change the type of input from radians to degrees. It's going to be a little bit easier for us to manipulate this. And you'll see that now it's moving slightly. So this is actually half a degree rotation, but it's very small. And also all of the floor plates are rotating with the same default value. So first thing, let's construct a slider for us to see how the general component works. Then we will provide specific values. So go ahead and construct a slider that goes from 0, less than 5, less than 180. Go less than 5, less than 180. And connect this to the angle. So 0 angle for rotation, there's no rotation, and then you're able to rotate, in this case, to 180. So that's fine, but we're doing a general rotation. If you remember what the absolute tower looks like, every floor is slightly rotated. So if you remember this idea of every floor having a specific value is what we just did with our series component. And as you can imagine, I'm not also going to provide 56 unique values using a slider. So we're going to use a series component again to tell it what is the interval of rotation every time that our tower is rotating. For the to reduce confusion, because right now not only we have the move component but also rotation component, and because Grasshopper always leaves a trace behind, let's click on our move component, right click on it, and turn off the preview. So when you turn off the preview, which you can also do by selecting and using the shortcut Control Q, you are eliminating that preview. And again, you can quickly see the difference since the color of the component turns darker. Now I'm only seeing the rotated floor plates plus the base floor plate here. So I'm going to also click on the initial ellipse and Control Q to turn off that. So I'm only seeing the output of the rotation. So next thing we're going to do is we're going to find another series component. I can either copy paste what I already have or go back to our set menu under sequence and look for another series component. And if you remember, series component starts from 0. Then every step we can provide a value. So every time what is the difference, and then when is this step ending. So when this is ending, because this is about rotating the floor plate, this is already determined by this slider, right? So this slider determines how many times I need to repeat this for my floor. So let's go back to the slider and actually change the naming and call this one is number of floors. And this number of floors determine how many times we need to repeat this. So let's take a wire from this slider and connect it to count, right? So how many times I want this floor plate to rotate uniquely. So we're using the same slider. Then for step size, this is, in this case, if we're translating to our angle, what is the difference between angle of rotation each time? And I'm going to use a panel here so you can see this better. By default, this is set to 1, so this is what I was using. I'm going to make a slider that goes from 0 less than 5 less than 10, 0 less than 5 less than 10. And what I want to do in this case, every time my floor plate is going to be rotated 5 degrees, right? Then what is the starting value? I'm going to actually keep this at 0. Since the first floor plate, I don't want it to move. And with that, I'm going to just group these together. Control G, and let's call this angle of rotation. And the last step here is to get rid of that one single slider and use the output of series and connect it to the angle input, and there it is. There's our twisting tower. So let's think about what is happening here. We start from the base, right? So the base floor plate, it is getting a rotation angle of 0. Then the second one is rotating 5 degrees, another 5 degrees, etc. And that rotation stops based on number of floors we have. And if you, as you can imagine, if you decrease this, so this is 0, there's no rotation at all. But as you increase this, you're able to actually increase the rotation. So with a very simple input, and we're providing a unique input here, we're able to have a completely different output. So this is a really interesting concept, and this is kind of introduction to how math architects begin to conceive variation of these tower, one next to another. For the sake of this tower and trying to replicate the geometry as much as possible, we're going to reduce this to 5 values. And last step, I'm going to group these together, and as you can see, I'm starting to see the color being repeated. And I can determine that maybe I want to keep the same color or a different color for this. I will go ahead and change the color. So for my variation of the floor plate, I have a slightly different color. And I'm going to now set this as a default, so then I will use the same thing for when we're working on the balconies. Okay, and the last thing I want to say that this is rotate floor plans. Our next step here is to construct the balconies, and the balconies are, although they're our next step is to construct the balconies, which are generated from the floor plates. However, they have a slightly different, let's say, distortion. So it's not an absolute offset. For that, we're going to learn a new tool under transform, under affine, and we're going to do a non-uniform scaling of the new floor plates. Let's grab a scale non-uniform. And in order to be able to generate this, I'm going to actually turn off the rotation component, and we're going to continue working from the move component. The reason for that is that the scaling is using general vectors in x, y, and z direction. If I were to apply that to the rotations, the x, y, and z is not going to be translated accurately. So each of them would require their own unique vector, which we need to generate. That would be a little bit more complex than what I would like to cover for this tutorial. So for that, let's go ahead and select our rotation component and turn off the preview. And let's go back and continue working from our move component. So right click and turn on the preview. And this is a very common way that you will be working. You will be generating and branching out from different parts. To move this panel here, and again, this is for our own reference. So we're going to connect the geometry coming out of our move component to the geometry input of non-uniform scaling. So if you think about scaling, you're able to use a scaling plane or a starting point, and you are able to scale in X, Y, and Z direction. In a uniform fashion, the ratio of scaling in X, Y, and Z would be the same, which is what by default we have here anyway. So in this case, we are seeing a duplicate of the same thing. However, if I want to do non-uniform scaling, I would then vary these inputs here. And scaling, the way that is determined, scaling of 1 is the actual scale. So think about it as 1 being a multiplication of, in this case, if we're looking at percentage, 100. And let's say a 0.5 scaling would be 50%. And let's say if I want to double the scale, I would do number 2. So that would be 200% of scaling. So before that, first thing I want to determine is I want to determine the scaling plane. So by default, always the scaling is determined from the origin. So in this case, there's a default setting here. However, if you want to stay true to the geometry, you would be extracting, let's say, a centroid or a reference on the geometry itself. So for us to do that, I'm going to go to our Surface tab, and under Analysis, we're going to look for a component called Area. And this is a very popular component. You will be using it in different capacity because what it does is it takes a closed, in this case, planar or a geometry that the area could be calculated. Sometimes that's not always a planar geometry, and based on that, you are able to not only extract the area in whichever units you're working in, but also the centroid. So connect the centroid to the scaling plane. Now our object or our geometry will be scaled towards its own center. So we have as many, in this case, ellipses as we have centroids for them to have custom scaling. The next component here that we're going to be needing is a scaling factor. So let's create a slider that goes from 0.5 less than 1 less than 2, 0.5 less than 1 less than 2. And just remember that these have a preset of 1, but if I were to change this value, you'll see that we'll be able to then change the scaling. So I'm going to look at this from top view for us to see this better. So you'll see that now in X direction, I'm able to do non-uniform scaling. Right? And we can do this in all of the directions as well. After studying the plans, what I've determined here is that scaling of 1.1 for X direction will be appropriate. For Y direction, actually there's less of a distance from this end, so we need to just modify our slider slightly. For X scaling, that would be fine, but I can modify it here before I make a copy. So I'm going to right click and go to Edit. And instead of adding retaining this 1 decimal value, I'm going to add another decimal value. And with that, I'll be able to then do further modification. So just remember that initially I created my starting number as 0.5, so that only gives me 1 decimal value, and I want to increase that. There it is. So I'm going to then make a copy of the slider, connect it to Y value. So right now in X and Y value, they're the same. However, I'm going to double click here and I'm going to do that 0.5. So 1.05. And there it is, right? So from the side balconies, we have less of an offset, and then from the X direction, there's more. So let's go back to our perspective view. And if I were to disconnect the plane, let's see what happens. So I'm going to hold Control to disconnect. You'll see that it actually stays still the same. So this is due to the fact that we're still using the X-plane as our starting point. But this is a more accurate way for us to begin to work. So I just wanted to let you know that anytime that you're doing the scaling, you want to to be careful, or if you see any issues, is because you need to provide the centroid. So for the sake of this assignment, let's go ahead and also extract the centroid. So provide that as the plane. So this is our non-uniform scaling of the balconies. I'm going to group these together. And I'm starting to see that again, I'm inheriting this color. So I'm going to actually do Control Z. I'm going to sample this color. Maybe I can use this for my subgroups. Maybe Control Z. And I'm going to say this is a non-uniform scaling. And this gives me the balconies, but I'll determine that later. Then the next thing I want to do is I want to also rotate this based on the same rotation value. And just remember that the reason that I'm doing this separately was because I wanted to initially scale them to based on X and Y. So I can just make a copy of this component or grab a new one. Since this is already set to degrees, let's do that. Select the component, Control C, Control V. And when you do that, I'm inheriting not only its input, but also its preview. So darker gray means that the preview is off. That's fine. It's still connected to the angles, which is, that's exactly correct. So you want to just replace the geometry with the geometry input. And last thing, I'm going to turn on the preview. Just remember that we already have this on, so we're going to see a double, and we just need to flip this. For that, I can either turn this off, turn this on, but since they are already in the state, actually the opposite of what I want, I can select them together and do Control key. And there it is. So right now, I do see the balconies also rotated. Just keep in mind that I also have this preview of the original ellipses. So these are determined later on by the way that floor plates are set up. So let's go ahead and also turn off the preview. So these are just the balconies, but perhaps we'll see this better if I also turn on the floor plates, right? So right now we see not only the floor plates, but also the balcony, let's say boundaries also rotated. And we could definitely see the relationship between them. So this is a very common practice you will be doing, that you constantly will be manipulating your preview. And this is something that you will get used to over time. Sometimes it might look messy. If it does, just take your time, organize, and make sure that you have the appropriate preview on. So last thing, I'm going to group this rotation to here. And I can again sample either, let's say in this case, this color, if I want to keep it the same. And I'm going to say that this is my, I call this one rotate floor plates. I'm going to say this is my rotate balconies. Alright, so we have the floor plates, we have the balconies. Let's continue. Next thing I want to do, I'm going to take the balconies and I'll start off by extruding them. Let's begin to build a floor plate. And if you think about this, balcony is the extension of this, so chances are that your floor is not disconnecting, and this would be kind of, the balcony would be the larger floor plate that then is stacked based on the vertical load transfers. So we're going to take the boundary here, and I can either extrude it first, then cap the geometry, or I can create a planar surface first and then extrude that. Let's go ahead and do that first. We're going to go to our surface tab under freeform subtab. We're going to look for a component called boundary. And what boundary surface does, it creates a planar surface, and it takes basically any planar geometry, and there it is. So right now we have surfaces that are running through here. Now, as you can imagine, we need to create an extrusion of this, so we're able to provide some thickness. So let's find an extrude component under surface freeform extrude. And in this case, extrude not only it needs a base geometry, but it also requires direction. Just one note here, you can extrude curves or surfaces, so it doesn't really determine the geometry. But if you hover over it, it tells you that this could be a curve or it could be a surface. So the direction is in Z direction. I'm going to go to my vector tab, vector subtab, grab a unit Z vector, and by default this value is set to 1. In this case, 1 foot. I want to make this actually 1.5, so about 18 inches. And I'm going to just double click, create a slider that goes from, let's say, 0.5 less than 1.5 less than 2, and I can determine the thickness. I'm going to keep it at 1 for 1.5, connect it here, and that has a closer thickness to what actually this tower is doing. I'm going to group these together, Control G, and these are my floor thicknesses. Glazing between each floors. So let's go back to our floor plates here. Now, if you remember, we just actually created thickness for each of the balcony plates, and if we are doing this accurately, so the glazing should meet the floor itself, right? So we have to actually move this up slightly, which is determined by this value here, before we begin to then extrude between each floor. So let's go ahead and first move these by this value. So we're going to grab the move component by going to our transform tab, Euclidean move, and so we want to move each floor. How much we're moving this is determined by this vector. So in case we change our mind about the thickness of the floor, I can use this vector. So there's that. If I look closer, you'll see that that's what we have. Then the amount of extrusion, this is going to be determined by what our floor to ceiling height is, which is 15, minus the amount that we just moved up, right? So this is a simple operation, maths operation. So we're going to go to our maths tab and go to operations or operators, and we're going to use a subtraction. And what we want to subtract is our typical floor to ceiling height from the thickness of our, in this case, balcony floor plate. That becomes what we're basically building on. So that becomes the new z value, and I still need to then provide a unique z value here, right? Because this one is basically inheriting the value from here. So let's go to our vector tab, our vector sub tab, and grab the new unit z vector. So that becomes the new floor to ceiling height for our glazing. So then that becomes the new vector of extrusion. So we still need an extrude component similar to this. So let's go to our surface tab, our freeform sub tab, extrude. And what I want to extrude is these floor plates, which we're going to provide as the base geometry, and the amount of extrusion is determined by this vector that we just constructed. There it is. So we should see that actually these are comfortably sitting between each floor. Alright, so I'm going to now group this bunch together. And Control G, and this becomes glazing for each floor. Now that we have all the floors and balconies, we will look at how to separate 3 floors towards the ground. That becomes the entrance lobby, and 3 floors on top. That becomes the rooftop space. Let's do the definition. Let's try to understand what we have here. So we have a series of floor geometry and balcony geometry, and then we're extruding and providing thickness. So if I want to manipulate my data, meaning let's say if I want to separate the 3 bottom floors and 3 top floors, the place where I'll be adding these operations and these let's say data operations will be here, right? Because after this we are just working with the data that's generated. So to perform this next part and to not cause any confusion here, we're actually going to separate these wires. So then we're only left with the geometry that is basically the basis of what we need to manipulate. I can go ahead and and let's say turn off the preview, but I want us to just purely focus on the base geometry first. So to separate these wires, and again, this is the floor plates and then this is the balcony. So we don't need to worry about the other sliders. We can either right click on the input here, go to disconnect and disconnect from here, or if you hold control and see this red arrow appearing, you can also separate the wires from here. So after I do this, I go back to the basic wire frame that we had. So I'm gonna separate these slightly so then we can work here. So let's start from the floor plate, and I'm going to turn off the balcony so we're only looking at the floor plates, but the operation will be the same and we'll be repeating it for the balconies as well. So select the balconies, and you can either right click or turn off the preview, or select and use Control Q, which acts as a preview, turn it on and off, but in a Boolean format. So if you remember, we have the centroids extracted, and these are the centroids of the balconies, but actually they do correspond to the floor plates as well. So we're going to take advantage of this, and we're going to visualize the order, and that would allow us to understand what is it that we want to separate. So let's go to our display tab, and under vector subtab, look for a component called point list. And this is a really useful component which only provides preview, and we're able to connect the centroids here. And then provide us a slider for size, and we're going to be able to actually see the index number much better. So create a slider that goes from 0.1, less than 1, less than 5, and we're going to increase the size until we can actually see the numbers a little bit better. Actually, I'm going to increase this a little bit. I would right click on the slider and go to values, and instead of 5, I'm going to make that 10. So I can just select the 5 and drag it up, or you can just double click on this bar and enter the number directly. Either case, it's fine. And this just allows me to increase the size a little bit. So what I want to do is I want to actually from all the list of floors, I want to be able to manipulate the first 3 separately. In this case, what I need to do is to just extrude it straight down, but I'm going to keep the rest with the structure of the extrusion that we have. So under our sets tab, under list subtab, we have number of operation that allows us to work with order of our data. So for instance, change the order of the data, or in this case, split the list. So a list could be a list of curves, a list of surfaces, or polysurfaces, it doesn't matter. Anything that is set up with the structure of the list. In this case, if I grab a panel, you'll see that it shows me that there's number of geometries. So in this case, elliptical geometry with an index and with a path. So as long as it has the structure, I'm able to work with this content here. So we're going to use this component called split list. And if you look at the icon, what it does is it takes a list, and based on an index number, we can break it into 2 sections. And that's going to work for us because we're going to then treat the curves down here separate from the curves above. So if you feed the input to the list, the index number that I want to use for separation, in this case, it's 0, 1, 2, 3. So I'm going to use that as my splitting point. And this is why we're printing the numbers. It allows us to see that. So I'm going to make a slider that goes from 0, less than 3, less than, in this case, we have 56 items, 56. So let's see what happens when I'm splitting this. I'm going to give myself a little bit more room to see the outcome. And you'll see that now I have 2 different lists. So the first one, it gives me the bottom 3 that I have. So I'm using that number 3 as a separator. Then the option B gives me everything else, right? So in this case, it gives me the rest of the components. So right now, this component gives me both of the lists, but if I use a container here, it would actually allow me to look at the geometry separately. So here I have curves going in. So if I go to my parameters tab under geometry, I'm also going to grab a curve container to split the geometry. So if you grab a curve container and feed this to the outcome, now you can clearly see that I'm able to separate the geometry here. And then if I use the same thing, I can just use another curve container here. Now this gives me everything else, right? So this everything else is then what I could use. Alright, so we have this part set up. Let's also do some meaning here. So this one splits it based on, I'm going to group this to itself, go Control G, and we're going to call this, entrance lobby. Rotates. And this one, Control G, we're going to call it apartments. Now, this is the bottom one. These are the apartments. But if you remember from the image, actually also the top three were separated. So in this case, I would actually need to do a similar operation to be able to separate the top ones from the rest. In this case, the rest of the, in this case, apartment floors. So I can do this in a similar fashion, or I can also use another method for separating the top component. So I'm going to use an alternate method so you know that we can use one or the other. So one way will be similar to what we did here. I can do another split, and I can split, let's say, from 52, and we can get those components, right? Another way I can treat this is if I separate it based on the index. So let's try that. Let's go to our sets under list, and I can use a component called list item. And from these components, I want to split certain indices. Now, we do have to remember that actually these numbering is coming from when we're looking at all of the elements. So we're going to actually migrate this down, and then we're going to do a new numbering of our components. So for the apartments, which is still missing 3 components, let's extract its own vertices. Then we're going to display the number. So we're going to go back to our surface tab, under analysis subtab, grab another area component, so exactly the same component we're using earlier. And again, this what it does, it allows me to extract the centroid. And then this time I'm going to look at the centroids. And here we see that, yes, the number definitely changed. Apologies for the number of components here, the wires intersecting, so you have to always just try your best to clean things up. Okay, so we split the list. These are the lobby curves, these are the apartments, and then we name the indices. Now I'm able to look at the indices here. So then if I were to feed the apartments as a list, the indexes that I want to use for separating these would be index 50, 51, and 52. So the way I can do this, I can create a panel, and I could say that give me index, let's say 50, enter 51, enter 52. And once you're done entering the indices, then you can come out of the panel. Then you want to right click on the panel and click on this option called multi-line data. And what it does, it actually takes the data as one entry, turns it into number of entries, right? So now these are the indices that I want to separate. So 50, 51, and 52. And you can just continue adding to this, or you can extract another index if needed. So if you connect this to the index input, and if you select this, you'll see that sure enough, it's selecting these top elements, right? So if I look at the bottom one, actually we separated now these 3 using the split list option, and you'll see that we can do a similar outcome using another method. So it all depends on what you prefer in terms of let's say, operation that you want to do. Okay, so first I'm going to just group this together. So we're using this as a reference. So for this, we are extracting centroid points and displaying order. Then I'm going to group this together. This is extracting 3 top floors. So as you can imagine, when I'm extracting the 3 top floors, but I still, have all of the curves together. So if I want to then create a balcony, let's say here, I actually cannot use this, right? Because this one just selects all the 3. So just like here, we can select only certain numbers that we want. There's a similar component that allows us to use the same method, same numbers. However, this time we're going to exclude this from the list, right? So then we're going to be left with everything but this number. So I want to show you also that method as well. So if we go back to our sets tab, right next to where we grab this component called list item, we're going to use another component under sequence called call index. So we're going to remove these indices using this component. So that's under sets, sequence, call index. And in a sense, it looks quite similar to the component that we used here. And in a sense, it takes the same input. It takes a list of curves, right? So this is what we have here. It's looking for an index, or in this case, indices. So number of indexes that we want to extract, and it's going to remove those components. So let's try this. I already have this indices separated. So connect the same panel to the indices. And you'll see that, yeah, sure enough, this time it separates everything but those floors, right? So we're able to now separate apartments. So this is extracting 3 top floors, and I'm going to group this to itself and say this is extracting everything but the top 3 floors. Okay, so we are getting there. I'm going to select these panels and delete them since they're taking up too much space, and let's sort this a little bit. And as you can imagine, these extractions are pretty much what I want to use to then create the floors, right? So if you remember, this was the bit that we used for creating the glazing of the floor. So all you need to do is to now replace the previous geometry, which was connected here, with the new list. So connect the list to the geometry input, and there it is, right? So it only creates the glazing for those sections. So let's group this part together so we're able to begin to separate, because we also need to do the similar process there. So I'm going to move this down here a little bit to take a few minutes to organize this. And I'm trying to kind of create a separation between these and what we're going to be doing on top. And I'm going to then group everything together here. Control G. I'm going to begin to change the color here, just so that I'm able to distinguish, let's say. Okay, so we are set here. Now we're gonna move on to do the glazing for the bottom part and for the top part. So let's look at the information we have. These were the curves that we used to extract. And if you, let's say if I look at the hover over, these are basically 3 different circles that are selected. So in this case, I'm going to grab the circle on the floor, and I'm going to use that to just extrude up. And we're going to use a similar component that we use here another list item component to just separate this the first one, the one on the ground. So let's go to our sets, to list, grab a component called list item. We just use that here. And I'm going to connect the curves that were separated here. So these are the bottom three. And in this case, you can see that by default, yes, sure enough, it's extracting index 0 because that's what it has by default. But I want to make this explicit, so I'm going to make a slider that goes from 0 less than 2. And I'm going to connect this here. And if you just select the component, it would highlight what's selected. And by, let's say here, going through them, you could see all the options, right? So for now, let's just keep this on 0. I'm going to just group this to itself. So this is extracting base floor. Then I want to extrude it all the way up to up here that it hits or it covers the 3 stories. So we're going to use extrude component under our surface, freeform extrude. And we're going to extrude in Z direction, and that's a vector subtab, unit Z. And the amount of extrusion will be determined by the height of each of the floors. If you remember, we determined it here, 15 times number of floors that we have, which is determined by these sliders, right? So this is what we're using to split. So this could be a multiplication operation. If we go under maths operator, we can use a multiplication. So just keep in mind that any of these operations, if I, instead of, let's say, grabbing a multiplication component, if I use then I can get a multiplication. Likewise, if I do slash for division, or let's say plus sign for addition, or minus for subtraction, we can easily just also use these as shortcuts. So let's go ahead and grab a multiplication from maths operators. Multiplication, and what I want to multiply is height of each floor, so that's 15. So connect that to the multiplication and number of floors that we have, which is determined by these sliders, right? So then that number becomes the extrusion height. And there it is. You can see that now we have a floor to ceiling extrusion. And I'm going to just group these together and say this is entrance lobby facade. Okay, so if you want to just remember, if you want to just replicate this color, you have to make it a default, and then next time you group it, you will be able to do that. Or you can just determine a new color for grouping that you're creating. Okay, so we are set for the floor. We need to do a similar operation for the rooftop here. So in this case, what we're going to do is we're going to grab the top component and we're going to extrude that down, right? So let's go ahead and find that. So in this case, this is a component that we're working with. And if you remember, we extracted these curves using a list item component. So although I've, in this case, extracted item, let's say 50 through 58, but I am creating a new list, right? So the first item that I'm extracting, item 50 becomes the item 0, 51 is item index 1, 52 is index 2, right? So if I want to just select the top component and extrude it down, I need to do, similar to this, another list item component. So I extracted the top components, then I can also extract components from here. Now it is true that instead of extracting all 3, I could have just extracted the top component, but I do want to show you different ways that this operation can be conducted. So let's grab another list component item here. So under sets, under list, grab another list item. And in this case, I'm going to run this again. And if I select the first one, which is the 0 by default, that is what's associated with that number 50. So for me to grab the top one, that's going to be this number, right? So if this is 0, I need to grab item 2. I do want to, however, show you something. So for this, let's go ahead and create a slider that goes from 0 less than 1 less than 2. So 0 less than 1 less than 2. So you are able to, separate this. You are able to select either one of these, right? So item 0, item 1, item 2. However, if you just keep the your first index to index 0, right? So that's the starting point. If you zoom in on this component, you'll see a plus sign that's appearing. So the plus sign allows you just to easily just expand on what you're constructing here. So for the sake of demonstration, I'm going to grab another curve container to separate the outcome so you can see that better. So right now I'm only extracting 1, but as soon as I zoom in and do a plus here, so right now it says whatever the I is, so I is a variable, is a placeholder for whatever the index might provide, so in this case 0. So if this index is 0, I plus 1 is index 1, so meaning if I connect this here, so that becomes, if that's 0, then that's plus 1, right? So sorry, this is 0, this is plus 1. I can zoom in again and extract another one. Now it becomes plus 2. So I want you to just be aware that there's a lot of components in Grasshopper, especially the ones that are dealing with lists. You're able to add a plus or a minus, and at any point you're able to also turn this back into its original, let's say, form. So for the sake of this tutorial, I'm going to actually get rid of this additional indices, and instead of working with index 0, I'm going to just go to index 2, and that becomes the top curve that we're selecting, right? So the purpose of this tutorial is to introduce you to a number of list operations as well as transformation. So we're going to do now another extrusion, but in this case we're going to extrude down. So we'll look at how to change the direction of the vector. So to do another extrude, we have already been using this component, so I'm going to go ahead and make a copy of these. And making copies are quite common when you have, let's say, you're repeating the same operation, right? So I need to extrude in the Z direction, and there's a certain height that's associated by number of floors. So I'm going to actually just select these, do Control-C, Control-V, and so that becomes something I can utilize, right? But if then all of this is dependent on the data, all I need to make sure is to just replace this with the new information, and you'll see that sure enough, this takes the top floor and it's extruding it up. But in this case, I actually want to do the opposite. I wanted to extrude down. So to think about extrusion, which requires a vector, it also has directionality, and this number could be negative or positive. So I can either turn the number into a negative number, or if we go back to our vector tab under vector subtab, there's also an option to reverse our vector. So that's under vector, vector subtab, and reverse vector. And you can see from the icon, it takes the vector as is and reverse the directionality, and there it is. So there's a couple things happening. So one is that we're seeing that the directionality clearly worked. The other thing we're seeing is that we have an issue here with number of floors. So I need to actually subtract number of times that I'm multiplying this value by the split number. So there's nothing really, let's say, binding us to this number. This is just based on what was happening on the ground level. Now, if I do want to modify this, I can just easily take that number and replace it with another one. So in this case, we're going to turn this into a 2. And because the 2 is a fixed number, I don't want to move around with the slider. I can also provide a number in a panel. So I'm going to do double click, quotation mark 2, enter. So I'm going to replace that with 2. So now if I look at the extrusion, there it is. Alright, so we're gonna also select these components, and we're going to do a Control G and say this is the, I'm going to say rooftop facade. Okay, so although I have all the components extracted right now, as much as it say pertains to the floors, but it's quite difficult to separate that. So we're going to use some colors and materials to identify them a little bit better. So let's go to our Display tab. Under Preview sub-tab, we're going to grab a component called Custom Preview. And when we're doing a custom preview, we can also provide a material or a color swatch. So color is one component of a material input. And with material, we have a little bit more flexibility. So let's look at the difference. So take the extrusions. In this case, this is the top portion that we've extruded, and connect that to the geometry input. And by default, it has this pink materiality. So far we've only used colors that we've got from parameters under input color swatch. If you go back to your transform tab under preview, we also have this thing called create materials. So we have a create material component, and it's a little bit larger than let's say a color swatch, but we're gonna see what it is. And as soon as you connect, you'll see that the same pink color that's associated with the color swatch or the default input of the custom preview changes a little bit darker, because think about it as there's a color, but the color could be matte, the color could be shiny, it could have transparency, so there could be other attributes here. So let's understand what these are. So the diffuse color is the base color, and you can see that it tells you that it's determined as hot pink. Let's grab a color swatch under parameters under input, grab a color swatch. This basically becomes the base color, right? So think about this as one of the, let's say, variables here. So in this case, if I want this to be glass, I'm going to make this dark blue. And certainly we can come back and change it. The specular is the color of your material when you have a bright light shine on it. So usually the way that our eyes perceive it, where you have the most amount of light, or whatever is closest to you, that is lighter. So in this case, this is set to white. We're going to make a copy of our color swatch, connect it to specular, and I'm going to actually turn this to the default, which is white. The emission color is the color that the shadow casts. So this is by default set to black, but this is going to make a large difference in your object. So for instance, instead of let's say creating color black, actually don't need to determine the transparency for this. If you begin to change this, you'll see a let's say stark difference in your geometry, right? So if you have let's say glass, and that's bluish color, but let's say when the sun is at a certain time, it might actually start to change its attributes. So this is something that we can play with quite a lot. Then the other thing is transparency. So transparency is a value between 0 to 1, and for this we can just use a default slider from parameters input. And in this case, 0 is completely opaque and 1 is completely transparent, right? So you can set this up, and as soon as we start to increase the transparency, we see the extrusion that we did beforehand. So I'm going to select and turn it off, and there it is. For me to also turn off everything else that's interfering, let's go down the stream. I'm going to select this component, which allows me to extract the top layer. Let's go forward. So these are the curves that I've extruded. So one by one, you can go back and turn it off. Then we have all of the curves for apartments. I'm also going to turn it off, as well as when I'm splitting the floors. And if I go upstream, this is pretty much everything that was rotated, right? So select and control Q. Now you can hover over everything and turn it off. So this is a preference that you might develop over time. I usually build this geometry, then go back and modify it as I find fit, right? So in this case, I'm just going to group this to itself, Control G, and let's call this glass material. And if you think about it, we also have a few other glass materials, so we can use the same for that, right? So the other glass material is all the extrusions, and what's good is if we just use the same material input, we can easily just modify one component and everything else would be modified. So I'm going to keep the material just in one place, but I'm going to use separate custom preview components. So again, going back to our display menu, or display tab, under preview subtab, grab a custom preview, and I'm going to copy it one more time. And one would be connected to the apartments, and this is also glass, and I'm going to use the same materials for this, so then it's easier for us to change. Let's say if we want to change a color, but then we need to go back and turn off everything that's pretty much changing or interfering with the preview, right? And this is something you need to just go back a couple of times until you do that. The last thing, this is the base, let's say, facade that we have, and we had developed that here. I'm going to move this down here since we still need to do the balconies. So in this case, I'm going to use this extra custom preview that I have. Connect it here, and again use the same materials so we can change it easily. Feel free to, when you're building geometry, you can definitely, for your projects, use separate ones. The reason that I like this method is because I can easily just change one value and everything else is updated. And for this lobby, I'm going to go back and turn this off again, and then go upstream. That's right. So it seems like it's there. We're able to create all of these panels. So I'm going to take a moment and modify this a little bit. I'm going to take this custom preview and add this to this group. So select, right click, and add to group. Same thing with this one. Select, right click, add to group. I'm also going to add this to this larger group. So select the group, right click on the larger group, tell it to add to group. So what you see is, depending on the order of selection, sometimes you might see something like this, that it looks like something is behind the other. So if you then click on this larger boundary, if you use Control B to send it back, so think about this as illustrator layer, right? So then that larger group is sent back. Let's go ahead and apply the same thing to our other components, in this case rooftop and the materials. I'm going to select them and right click on the larger group and right click and add it to the group, and there it is, right? So this is basically everything that has to do with the floors. I can always continue adding components, and you'll see that now this becomes a larger group that I can work with. It follows the same structure, and we have generated that using an offset from the main filler plates. As you can imagine, the structure of the data is going to be similar. So I'm going to add this to this group and continue from here. I'm going to turn on the balconies here, so we're going to continue from here. And we're going to start off by replicating what we've done here. You could possibly copy and paste the components, as we're going to be using many of the same steps, but I want to create it from scratch for this for the balconies as well. So then this way you can also review, and you wouldn't be confused by copy pasting things and reconnecting wires. So let's follow the same step, which is creating a split for the list of balconies, and this would allow us to not have balconies where we have this entrance lobby. So go to sets, go to list, and use a component called split list, which we used earlier. So these are all the balconies, and the index number that we want to use for separation, we have the number here. I'm going to pull this up, and we're going to just reuse the same number. So there it is, that becomes the split. And I'm inputting list of curves, so the outcome could also is going to be also curves under parameters, geometry, and the graph curve container. So this is going to be the curves that are basically part of the base, and then everything else. I'm going to make a copy of this, Control C, Control V, connect here, and there it is. So as part of our base construction, actually, although we don't want these two geometry for creating a balcony, I'm going to extract the base, so then this way we can treat this as a foundation. And for that, as you can imagine, we would be needing to extract information. Now, earlier we renamed the indices based on extracting the information from the split list. So at this point, I'm not going to change this here. I'm just going to select and turn off the preview. So we're starting from, let's say, clean here. We're going to go back to our centroids that are feeding into scale geometry, and we're going to then display the order here. Again, this is the point list, and then determine a slider for size. So I'm going to do 0.1, less than 5, or less than 10. And there is the size component. You can see that in this case, I want to extract item 0. So then that becomes the base. So from this, select your component, which is under sets of the list item. And basically, whether I use this list, right, so list of all the curves, and that's pretty much what the index I'm seeing. But then also after I split this, the first item would be the same one, right? Because this is the beginning of the list. So that becomes the base geometry, and I will be able to then extrude that on its own separately. So this extrude component that we have, I can already just provide that here, and that becomes the base. But if you remember, this one is for rest of the floor thicknesses, so I can actually make a copy of this, Control C, Control V, and I'm going to just keep one connected, and instead of floor thickness, I'm going to call this base thickness, and I'm going to then disconnect it from floor thickness. To disconnect, since I have more than one wire, I can again go back here, go to disconnect, or hold down Control and disconnect, right? So then we can use that for rest of the plates. So for this, I'm going to just add these to the group, select, right click, and add to group, and there it is. If you are thinking that our colors are becoming similar, you can definitely start to change the color of the, let's say, balcony components. And I can also make that into a default color. So then if I were to regenerate the group, I'll be able to then keep that. So in this case, I'm just copy pasting the name, so I don't have to retype it. To continue with the extraction of the curve from the roof, let's analyze this before we do that. So first, I want to go ahead and update the indexing. So if you remember, the index that we're displaying right now is still reflecting all the curves, and I want to only reflect the ones that we have separated after subtracting the ones on the ground level. So for that, basically, these are the updated curves. So I need to extract their centroid by going to Surface, Analysis, Area, and the point display that I want to do then needs to be generated from here. So it's basically going to be those values minus 3. So I'm going to just copy this, Control C, Control V, you can generate a new one, and just display them here. And obviously here I'm seeing an overlap. I'm going to go back and turn off the views here. While I'm here, I might as well just add that to the group, right? We're always trying to clean up the definition as much as possible. And there it is, right? So if we're thinking about this as a rooftop component, there's in the images, what it seems like is that this is a rooftop part of the building, and then there's a cap on top, right? So for the sake of this tutorial, we're going to look at how to keep the top, keep everything else, and just extract this item 51. So earlier, when we went through this exercise, I showed you how to remove and how to also extract, right? So with list item, we're extracting. With a call index, we're removing. So in this case, the call index method would work. So we're only going to remove item 51. So let's go to our sets under list. Under sets, under sequence, and grab a component called call index. And what I want to remove is from this list of already split lists, right? And the index that I want to use is index 51. So I can just double click, do quotation mark, 51, enter, and that's the index that I'm removing. So for now, if I select this, I should have everything except for that level, and that's good enough for us to just take these curves as is and connect it to our floor thickness. And you can see that now we're able to see the top that one level removed. So we have kind of a roof system, but you still have the balconies, right? Let's go ahead and first turn off all the curves that we don't need to see anymore. So I can pretty much window over this part, everything, and you can use your middle mouse button to turn off everything. You can also do them one by one or use your Control Q shortcut. But there's certainly, the downstream, there's more components that I need to turn off. Then similar to what we generated earlier, we're going to create a material with a custom preview. Since I already have this set up, I'm going to just select the group. So you can just window over the group, do Control C, Control V. And I'm going to just use this for the floors, right? So obviously this says glass material. I'm going to switch this to concrete material. And I'm going to take, in this case, we're just starting from the base, connect it to geometry. And instead of this color, which I already do see a preview, I'm going to select and Control Q. Certainly if we're using concrete, we don't want to keep it opaque, so there it is. I'm going to use a darker gray color. So here I can go darker, and also I'll change the emission color, which is the shadow color, to darker color. Then I could use something similar for the rest, or the same tone. So the best would be if you just use custom preview component to select the custom preview, Control C, Control V. And we're going to just replace the component. Now I'm seeing all the floors with the same color. This preview overlap is from here. So we're starting to see that basically as we go forward, we need to go back and turn off the previews or items that we don't need. So just select and do Control Q or middle mouse button and turn off. And that's about it right now, right? You could definitely change the colors. Okay, so the last thing we're going to do, we're going to first organize our components. Then we're going to create these balconies around the floor plate of the balcony. So we're going to create basically an extrusion from here, so it looks like the tower. Let's go back here and organize this a little bit. So here, this is, I'm going to call this remove lobby floor plates. Then here, this is point order display. I'm going to keep zero, Control G. This is remove rooftop balcony layer. And that seems about right. Then at the end, I'm going to just create a larger group with this. I'm going to just sample this light color right click and I can just make it a default color. Then use the Control G and give it a larger name or just keep it as is, right? Okay, so for the next step, as I said, I need to basically take this top curvature and extrude it out. And if you remember the way that we generated these thicknesses, so if we look at this is basically the floor thickness, right? And then I only want to do that for these floors, right? So the middle portion. And where do these come from? They come from these curves that we had to extrude, and the extrusion amount is 1.5 meters. So if I want to extract the top curve, pretty much if I take the same curves and I move it up by the same value, then I would be able to utilize those. But we're going to learn a component that would allow us to extract information from, in this case, your BREPs. So in Rhino, we are distinguishing our objects between surfaces and polysurfaces. In Grasshopper, this term polysurface does not exist, and the term polysurface is, let's say, translated to BREP, which stands for boundary representation. So think about it as a number of surfaces. So a polysurface is represented as this concept of BREPs. And if you go to your surface tab, a lot of the components that you'll see, they are for surfaces or BREPs, so that boundary representation. So just think about it as a polysurface. And under surface analysis, there's a number of components that would allow us to, let's say, extract information from a surface or a polysurface and do further analysis. So for instance, if we use, let's say, a wireframe component or a BREP edge component, we'll be able to extract information. So let's try this. To use this component called BREP edges, and what it tells you is that we're going to connect to a BREP, so that's the BREP as is. Then it replaces a number of curves. So the naked edges are the edges that are open. So as you can see that we don't have any naked edges, so this would be something you would want to test when you have meshes that you want to center through. You can take the interior edges do exist, and you can see that it's dividing it as line-like curve. So the line-like curve should be the seams. I'm trying to find the seams. Basically, that should be the segment. There it is, right? So those are the seams, the edges. And then it gives me a top ellipse and a bottom ellipse, right? So if I were to just extract the top ellipse, I'll be able to then use them for generation of balconies, and that would be an extrusion. There's also another component on their surface called a wireframe, which would give me a similar output. Let's compare them. And this one returns a wireframe, and you can see that it's pretty much the same thing. So this is a generic component. This one you would be using it to if you have naked edges as well. Additionally, there's another component under surface analysis called the construct BREP. So think about this as an explode component that allows you to then connect the surface or a polysurface, a surface, and a BREP. And this one not only returns the edges, right? So it not only returns the edges, which is again similar, but it would return the faces, in this case the surfaces, but also your points. So you can see that the extraction of the points in this case is the beginning and end. And this could apply for a surface or a polysurface. For today, we're going to just use the simple wireframe component as it's kind of a simple way for us to see what we're working with, but I wanted to also introduce the other components. So what we need to do is from all the branches, and we can start to see the dashed line, it means that information is stored in a branch, meaning I already not only have the extrusion, but now I'm trying to remember each extrusion when I'm extracting the wireframe has 3 items, right? And if we go to our parameters under utilities and use a param viewer component, which we often use in conjunction with our panels, you can see that basically it tells me that now I have that many branches, so 52 floors, 52 branches, and if you double click on it, that's the branching structure that we see, right? And you should see probably that we have quite a long path. So the path is the address we're accessing the information. Well, what that means is that we have generated a quite complex geometry, and step by step this path is being added. So for instance, if I go back to the very first one, you can see that the initial ellipse has one level, and then as you go more forward and we are doing more operations, you see that these paths are becoming more extensive, right? We don't need to worry about that for this tutorial. Just understand that this is an important component if we ever want to access the information. So from each branch, what we need to extract is the top curve. So let's go to our sets under list, grab a list item component, and I think if I select this, as you can see, the first one is ultimately the edge. So then I need to see, well, what about the other one? So let's make a slider that goes from 0 less than 2. And when you do connect this, if you just select the component, it highlights it, right? So then the next one is the top one. So definitely that's the one we want to group it to itself. And I can also just, let's say, sample this. We do this part and say that this is extract top curve to generate balconies extrusion. Alright, let's leave it as is. Before we begin to extrude this, I should also remember that when we generated this, actually our list still contains the cover, right, that covers the rooftop. So if I were to extrude this, actually this would also have an extrusion, and I need to actually exclude that from the list. So let's take a look at what we have here. Due to the fact that I had to do a frame extraction, our data became divided into a number of branches. So right now, what I'm working with is actually a branch structure. So the same index number that I was using before, now that has been translated to the branch structure. So if you look at the data, so these are the index numbers that have turned to a branch number. But if I look at the branch numbers, here it went all the way up to 52, but here I have only 51. If you remember, we excluded that, right? So this and the numbers are indication of the previous data structure. So there's definitely relationship between data that's maintained. However, with this structure, I'm not able to use, let's say, something like a equal index to then remove the top. So we need to do an operation called flattening, which is going to actually take our data out of the structure and simplify that. So if I were to look at a param viewer, currently our data is organized into a number of branches, and that is due to the fact that I had to do an extraction that it required data to be sorted further. But at this point, that's not needed anymore, so we need to do an operation called flattening, which will find the component number sets under tree, flatten tree. And what flatten tree does, which is all the way up here, if you look at the icon, it actually gets rid of the branching structure, right? So this branching structure, which creates this division between our data, that is going to be taken out. So you could connect that to the input of the tree, and let me show you what my data would look like afterwards. I'm going to use similar or the same information. So there it is. So if you just compare your panel, it went from dashed line to double line, right? So it became a singular list. And likewise, if I look at a param viewer under params utility, param viewer, now everything is organized into a single branch, and my icon also looks simplified. So when we are flattening information, flattening could also happen within the component. So if you right click, you'll see an option here also to flatten. When you do that, you would get an arrow, and you'll see that that automatically changes the type of data that's coming out. So there's a number of operations that you will be using when you get a little bit more comfortable the icons within the component, but for the sake of this tutorial, let's just go ahead and use the data structure and the component for flattening. And again, once that happens, I'm able to look at the relationship of the components closer to what we had before. So I'm going to just group this to itself, and we're going to say this is flatten data tree and converge to one branch or one list. So think about branches and lists as the same thing. So it converts everything back to one list. So what's the benefit of this? Now I can begin to think about information that I have here a little bit closer to what I have. But again, if you remember, this is something that we're looking at beforehand. So if I were to just reflect the data structure as I have it, I could just extract the point again and do another point list. So very similar to what I have here. So I'm going to just make a copy of this, Control-C, Control-V, take it all the way here. I should remember before I do anything that I'm going to go back here and turn off the preview here. And I still do see this, but basically now I'm going to just replace that. So now we can clearly see what is directly reflective of our structure here, right? And if I do want to extract this one, so remove this one, I would just do a call index of number 51, which is the last item. So let's try that. We're going to go back to our sets under sequence call index, and the index number that I want to extract is number 51. Enter, and there it is, right? So it gives me everything we want. And here we're going to group this bunch together, and you can keep these as a reference to do a comparison. Going to do Control-G. Actually, I'll sample this again. Control-G. And this is remove top. Down here. There it is. This one is still floating. I'm going to add it to the group. So just as you go forward, just start cleaning. All right, so at the end, we have all of this, right? I'm going to go ahead and extrude this. So this is a simple extrusion to get the parapet under surface, under freeform. We're going to do an extrusion. We're extruding in Z direction. So at this point, you should start to see your machine learning Markov working here. So I can just drag and drop from here, which it always knows my pattern. Or you can go back here and go to vector tab unit C. And in this case, we're going to create a 3.5 foot parapet. We're going to create a slider that goes from, let's say the least we want to do is 3 feet, 3 less than 3.5, or less than 4. And those become the balcony extrusions, which is what the tower is known for, right? Last thing, we want to add also a glass layer to this. If you remember earlier, we utilized if you remember earlier, we utilized our materials here, so I can just connect it back to the glass. So I'm going to make a copy of our custom preview and then take the balconies and connect it to the input here. So we're able to see the same color, and then I want to do a bit of organization here. I'm going to select these and group, and this one likewise. And you want to then begin to turn off the preview of components that are not final preview, which is going to be basically everything downstream. Okay, so your final should look like this. You have a base plate, you have the entrance lobby, you have number of balconies that are extruded, then the top two levels are extracted, and then you have a cap towards the top. This concludes our third assignment, and this assignment was aimed to introduce you to a number of operations, and these operations were from transformations to also maths operation. However, as you notice, a lot of the focus here was on understanding data structure, and this is something that we will continue to build on. So feel free to play with the color and type of material that you want to generate. And for your submission, as long as you are happy with the color, just save your definition and submit it as is. You do not need to submit the Rhino file with this, and you are free to select whichever color you like for the submission. Just make sure that your floor subtractions and heights are corresponding to the values that we covered. Thank you.